So according to the law, you can see recording it's started.
What's the program of today?
It was scheduled to discuss the two tables shared by you, the DB tables and calculus. That was programmed, but even Mr. Santarelli told us that he can do some direct shows. So it's up to you, Engineer Ray.
Well, we spoke with Mr. Santarelli because I would like to have first a video published and then comment. And this was not possible. And also Mr. Santarelli understood that anyway, repairing the power supply to LNB of the receiver involved to change SMD components, that it is not so easy. So we are not totally sure until I don't see the video that it is totally helpful, but we'll see. But the video is not ready now, and I will not do it in live. So I suggest that we see a document related to the easiest way to manage DB, because DB our bread of every day. So I suggest that you open the PDF, and I suggest a totally different way to make lessons to understand well how much you understand. I would like to revert the way to make lessons. So you make, not you, Puyu, but Joseph, David, and the others, time by time, made the lessons. And so we can understand better which is the lever that we was able to make you understand. Because if we are going too fast and we don't realize this, we are all losing time and make a big effort to have only a limited result. I think it's better to go very slow until all the concepts are clear, and eventually return back and make more simple video on the topics. Because on the Asian training we realize this. So this is the document. I would like that each one of you read part of a document, so you will also improve your English, and then try to explain to himself and to the others, like if he was a teacher. I would suggest to start with Joseph, that has a PhD on electronics. Joseph, did you understand?
Excuse me, because I have to go sometimes outside or inside because I'm working also here. If you can just repeat what you said, and I answer.
So first question is why, if you don't understand, you only ask if I ask you to do something.
No, it's not that I don't understand. At this time, you've given me two jobs. First, to translate the big document. Second, to subtitle the document of Alberto. And as I was not every time in an area with coverage of internet, that made me lower to do it. So at this time, I'm not really in place. why when you ask me something, I don't, sometimes I'm not present, I go and I come. This is the reason. But if I'm stay in front of the laptop, no problem.
But if you are thinking to attend a lesson, you have to attend the lesson. So
Yes.
anyway, do you
now? I'm out of my country now. On the field, I'm at Burkina Faso.
do you see now the document on the screen?
Yes.
Okay. You want to read it and to comment and to try to explain like if you was a teacher?
Okay, I will try. Okay, so question, why using dB? Answer, the variation of intensity of many parameter range from extremely small to extremely large value dB scale logarithmic compress this range of values in limited numbers. That means we want to avoid many numbers, and logarithm is a kind of reducing the numbers, but in fact, it's the same we multiply a value to a bigger value, avoiding many numbers. Same result, but less number to write.
And also, I would like to ask you a question.
Yeah.
If I said to you 0.000001, do you
Yes.
understand this number or not?
Of course, I understand, but I have to put it in another way to avoid many zero. It means 0, 10, 10 over, in French, we say 10 puissance moins. So,
my answer is that I don't understand this number, because if for some reason one adds 10 or take out 10, it is always a so extremely limited number that in your mind I cannot figure. But if they said to me minus 10 dB and minus 10, and if they say to me minus 100 dB and minus 110 dB, I clearly understand and understand the meaning of what these numbers are related. Okay.
okay.
So this is the reasons.
Yes.
Our mind are not designed to manage very huge number and very small number.
Yes.
Compressing in dB, we can always understand the ratio between these values.
Okay. So it's a kind of summarizing this number in another way, but it's referred to what if we say this, you can have an idea of what it means exactly, avoiding many numbers, many zeros.
Zeros or 10,000 million, etc. And we always understand if there is a variation, how big is the variation, because we typically use differential. So I higher the power by 10 dB. It doesn't matter if it is 1 microwatt or 1 kilowatt, but the important thing is to understand the changes. Okay. And second, there is another big reason, and then you can read it now.
Okay. So I continue. The reason that both human, both electronic equipment responded to the stimulus of the parameter in logarithmic way. That's what you said the same. If
Are you aware? Did you even realize this?
Yeah, because now we talk about the DB and we talk when we use it and why we use it. So because in instrument, in equipment, the ratio or the value of changing something can be bigger than what we can find. So the best way for us, or the best unit to use in such situation is of course dB.
But did you realize that your body
Yeah.
working in the same way?
Yes.
Okay. So now there is the example of your body, and you can read it.
Okay. So I continue now?
Yes, because there is the example of how your body reacts to excitation from light or from sounds.
Yes. If not, for instance, we could not hear very low noise and be killed if someone is crying. Okay.
If the response of our body will be linear, this happens in this case. Okay.
Okay. Same applies, for instance, for the vision of light intensity with eyes. Yes. You will not see anything in the shadow and you will be killed during the daylight.
Of course, if the human body has had a linear response and not logarithmic.
Yes, yes, of course, of course. So that means linear logarithmic response is yes, I understand, but I don't know how to explain it. But we don't we know now why to have to make difference between logarithmic and linear, because in such case logarithmic is higher, response logarithm is higher than linear, which will make us very lazy or something like this in the reaction.
No. Logarithmic is more compressed.
Okay.
Linear is higher. Is higher. This is why you can be killed if I am crying now, or you cannot understand
Okay,
if I speak if I speak much with less volume. Okay.
okay, now I understand. I take notes. So we have to manage continuously value in dB logarithmic square rather than in linear square. Okay.
No, why for square you went in
Scale.
scale.
A square, excuse me, it's my bad pronunciation.
Scale.
Scale. In French, échelle. Is that true? Échelle.
Yeah.
Okay.
No.
Thank you.
No. Scale is scale.
Yeah, scale. Scale in French. This is I know what it is in French, but its name in French is échelle. Not échelle to claim, no, but échelle to make a report, a ratio, something like this. Scale value.
That's correct.
Okay, thank you.
Okay. So okay. Why you don't ask the others, and I want to hear every one of you if it is enough clear or if there are more on this part. So please ask the other, and I want to hear from everyone.
Dear colleagues, did you understand what I was reading? Or if something you don't understand, you can put any question about this if you don't understand.
Joseph, it is very clear at that point, and I have understood that our mind needs to interpret. Our mind is better in interpreting shorter forms of anything than a longer form of anything like so many digits and like that. So it is clear.
Okay, I would like to add that nature work in logarithmic scale. If not, everyone will be killed. Okay.
Yeah.
And
I see that Mr. Kuzani show his hands raised or not.
Yes. Mr. Kuzani.
No.
No.
He suppressed now.
Okay.
For the other is clear. I want to have your yes or no from everyone, because if not, our doubt is that sometimes you don't understand, but you don't want to stop, and this is an error.
Clear.
Oscar.
So, Pande, for you it's okay.
Yeah.
Kuzani.
Yes, but they are. It's okay. We can continue. Can continue and understand progressively. Can continue. It's clear.
Mr. Kuzani.
Yes, I'm following. What I've learned is that instead of we are trying to let the powers and into the DBs so that we can be able to remember correct, and the values in DB show that it's easy to memorize.
Okay, like now we show where you go in the school, what you do with the other normal numbers.
Yes.
Okay, Mr. Kuzani, you want to continue reading the next question?
Let's see. This is the one that starts with, do we have always, isn't it?
Yes.
Okay. Do we have always to have with us calculators or tables for switching between values in dB or logarithmic scale to values in linear scale, or the opposite? The answer, no. Like at the primary school, where we learn and memorize in the long-term memory of our brain, big numerical tables like 7 times 8 is equal to 56, or 9 times 8 is equal to 72, for instance. We can do the same with the dB, even with only a few values, and using them like bricks to compute the dB or linear ratio values. We'll explore the method here for power. Same principle can also be applied for voltage or other parameters. So,
okay, I ask the other if this is enough clear or they need more.
The way they have explained here, is it clear to us?
Hello, people. Can you answer?
Yes, yes, it is clear. The statement is clear.
Okay.
Clear.
So, Mr. Kuzani, could you continue with the last question?
Yes. The last question, will we really use logarithmic formulas like dB is equal to 10 log P over PR or 20 log V over VR? The answer, no. We will use only the 4 algebra operators like positive, minus, multiplication, or division. The trick is that summing dB corresponds to multiply ratio. Subtraction dB corresponds to division.
Okay. Ask if this is clear. And I have a question. What means VR in PR or VR?
Is it clear, group? The other. What we are being asked here, PR.
I think at that point it is not very clear.
Okay, so this is why my question. R is for a reference. Okay, you see that you have a ratio between, for instance, for power P over PR. Okay, and we have to switch in our mind from this ratio, where anyway there is a power for reference that can be watts, a milliwatt, or something else, and dB. So in the formula that we will not use, but we will use to switch between the two parameters, one that it is linear, it is power over power of reference, and the other are the dB. This is the only thing that now you have to understand from this respect. Is now more clear? Because in the table you will have on one column dB and one on another column P over PR, that it is the ratio of power. So you know that you increase by 10 dB the power, you will increase even by 10 times the power respect to the power of reference. But I think that the example will clear more this. The second, stop microphone. Okay. The second you have, we understand, is the trick. You don't have to know even what it is a logarithmic, but you have to understand, to use the bricks you will memorize, that summing in dB correspond to multiply the ratio. Who is making noise? Kuzani?
Let me switch my microphone off.
Okay. And subtracting dB correspond to divide ratio. Okay, is this enough clear? Or you want to ask questions? Okay, so David, you want to continue with the next question? And Puyo, you have to...
Yes, I can.
Okay. So Puyo, please show. Okay. Okay.
Question, how many values numeric tables do we have to memorize in our long-term memory to manage this? The answer is only 4 or 5 values. Then we
Okay.
can go and look at the table of the values.
Yes, this will be, of course, demonstrated, but it is now only an assumption that you only need 4 or 5 values. So we will see together how. Another question I have for you. Do you have, do you know what it is long-term memory?
Long-term memory, no, maybe you explain to us.
Okay, I give you an example. I have a very good friends, 40 years. Every day I compose with the old telephone. Maybe I don't know if you have one of these, but okay. Every day I compose his number to speak with him and to tell to him, okay, let's meet us at 4 o'clock in the afternoon in this side, and we will play with a bicycle, etc., etc. And I did this every day, not 10 times, 100 times. Okay, I only did one per day, but for years. And I tell you the truth, I all remember this number even if I don't do it from years in my mind. This is long-term memory. Every day you exercise only 1 or 2 times, and this stays for years in your memory, even if you don't use it. So if you want to keep in your mind in long term for years an information, exercise only 1 day, but for a long time. On the opposite side, there is a short time memory, that it is what you use only once and then you forget it. And I give you a counter example. You can repeat for 1 day 10,000 times the number of your of phone of your friends, and it will only stay in your short-term memory. You will remember maybe the day before, but then will vanish very quickly. Have you experienced this in your life?
Yes, there are some
Yes.
formulas. There are some formulas we have to memorize when we were at school, and maybe, for example, the color codes of resistance. We used some words in French to fix all these color, and when we see a resistance with color code, we just have to remember these words, these words, and also we can calculate their value. So for me, it's something that we have to never forget. We have to keep it in mind every time. That means long-time memory.
Fantastic example. It is like you remember the flags of a country. The resistors are the same. The first time you made the calculation, then you do so many times, 1 per day, and then you remember the flags. Okay, let's go to the values.
Examples.
Yes.
values to be memorized. Everybody, all of us are looking at the table.
Yeah.
Yes, we see.
In one column we have dB.
Yes.
In the second column we have power, the ratio of power to the reference power.
Yes.
0 dB correspond to 1.
Okay, but let's now take it only like a table and start with the first and easiest number to memorize. You can read.
The easiest is 10 dB because it corresponds to the same power ratio of 10.
Okay, we have a point where dB and power ratio is the same, and it is very easy to remember. And it is 10. So if you increase by 10 dB, also the power increased by 10 times. And now you can start to use this as a brick. Okay.
If we want to know how much is the power ratio for 20 dB, we can 20 dB equals to 10 dB plus 10 dB. In power ratio domain is 10 times 10 equals to 100.
100.
Equal to 100, yes. Again, for another...
Stop. Is this clear? We have done the same operation of 10 dB twice. That means that in power ratio domain is multiplying 10 by 10. So 10. Two times. I want that everyone say yes or no, very frankly, because okay.
Yes.
Yes.
This is
so,
yes.
If you don't understand this, of course, we cannot continue. Okay.
So adding in logarithmic operations means multiplying in linear operations. That's the base.
Yes.
Come on again?
Yes. Go ahead.
Again, for another value, 30 dB equal to 10 dB plus 10 dB plus 10 dB, which is equal to 10 times 10 times 10, which is equal to 1,000.
And you can continue in that way.
I have a question, Engineer. In French, I know, but I want you to give me the meaning in English, and I will let me talk to you in French first, and you will give me the. Lorsqu'on dit 10 multiplié par 10, ça fait 10 puissance 2, c'est-à-dire 10 avec 2 zéros, 1 avec 2 zéros derrière. Et lorsqu'on dit 10 multiplié par 10 multiplié par 10, il y a 3 zéros, ça fait 10 puissance 3. Alors, comment exprimer les puissances de 10 en anglais?
The ratio of, the rise to a value, raised to a value.
Okay.
Power of.
It means 3 raised 1 in the where we have 1,000. The values, if I want to express in the rise of 10, how can I explain 1 and 3 0?
Yes, that's 10 raised at the power of 3. in English.
Yeah, but you even don't need to use power. The power, because we want to only use the algebraic formulas.
Okay.
But he's using
So-
the basis of logarithm, so that's why he tried to express it as a power, and will meet with this figure. That's what he want to say.
Yes, yes.
Okay, can we continue?
Let's keep it simple as possible. It is
Okay.
called with
Engineer,
acronym KISS. Keep it simple as possible.
okay, Engineer Ray. So if again I would give an example. So again, if I say 40 dB, is it equal to 10 dB plus 10 dB plus 10 dB plus 10 dB 4 times?
Right.
Yeah. Yes.
Okay.
And we are now
Let me
using, we are now only one memorized value. But now we will go on the negative side and see what's happened with minus dB.
Okay. If we want to use negative dB values to know how much is the power ratio for minus 10 dB, we just have to know that negative value correspond in the power radio domain.
Sorry, it was a typing error.
Yeah, corresponds in the power ratio domains to division. Minus 10 dB in power ratio domain is 1 divided by 10, which is equal to 0.1. Again, for another...
is this clear?
Yes, it's the opposite.
Okay.
Yes.
Okay. So we can continue.
Again, for another value, minus 20 dB equals to minus 10 dB minus 10 dB in power ratio domain. This statement is not very clear, Engineer.
Well, minus 20 is you made twice the operator of minus 10 dB, okay?
I think the term which is not clear was what means power ratio domain.
It is only that you go in the table from dB to P to PR. Power ratio domain is P over PR. So it is the ratio.
The linear ratio between the two powers.
Yes, exactly.
Okay, let me read that again. Again, for another value, minus 20 dB equal to minus 10 dB minus 10 dB in power ratio domain is 1 over 10 times 1 over 10, which is equal to 0.01.
Because it is 0.1 multiplied by 0.1. 1/10 is 0.1. Maybe I have to add another part and say before.
It's written here. It's written here.
Yes. Okay. But then I have, after the first part, I have also to be more clear in adding 0.1 multiplied by 0.1 equal 0.01. Yeah.
It is easy now to know the value of 0 dB equal to 10 dB minus 10 dB in the power ratio domain is 10 divided by 10, which is equal to 1.
Is this clear to everyone?
Yes, of course. I can add
Yes.
things. We can consider all the signs, I mean plus and minus, on an axis between 0 to the right and 0 to the left. And if we take 0 as reference, 10 dBs is 0 to the right, minus 10 dBs is 0 to the left. Left divided by right, it means 1. That's how I understand this line, this last term.
So you understand or not?
Of course, I understand, but I made a picture in my mind.
Okay. So now on the table, we have a second value to memorize in our long-term memory. Or we can, if we don't remember, we can even take a pen or make in your mind this calculation to derive it. Okay, so 0 dB is means that the power is equal to the reference power. Say that you understand, or more or less.
Yes, it's clear.
That we understand.
Get it.
Okay, so we are now at the second value, and now let's proceed.
The third value we have to memorize is 3 dB. That in the power ratio domain is 2, means double the power.
Okay, I think that every one of you, it is really the first value that you put in your mind, because maybe at school they tell you, okay, they show you the logarithmic, but then at the end, it is when you double the power, you have 3 dB more. Do this happen to you or not? So I go from 1 kilowatt to 2 kilowatt in the transmitter. How many dB I gain?
3 dB.
3 dB. Then I doubled from 2 dipoles to 4 dipoles. How many dB I gain? The same.
If are identical, the same.
3 dB. Every time I double my power capacity in some way, and every time I get 3 dB more. Or if I decrease, you get 3 dB less. Okay, please go ahead.
With this value, we can easily calculate the value in the power ratio domain of 6 and 8 dB. 6 dB.
Show why.
6 dB equal to 3 dB plus 3 dB in the power ratio domain is 2 times 2, which is equal to 4.
So 6 dB, sorry, don't go rapid. So 6 dB means in the power ratio linear domain means 4 times, like it's written here. Because 6 dB is 3 dB plus 3 dB. In a linear domain, it's 3 dB, it's 2 times. 2 times multiplied by 2 times means 4 times. So 6 dB is 4 times linear. It's written here. 6 dB means 4 times.
Yeah, but written is a table that you need to have. In the other way, you are only using your mind to derive the values. Okay. We can continue with 9 dB.
9 dB equals to 3 dB plus 3 dB plus 3 dB. In power ratio domain is 2 times 2 times 2, which is 8.
Okay. Let me ask you. I have a dipole, only one dipole. So the relative gain of the dipole respect to a dipole, how much dB is? Gain of a dipole respect to the gain of a dipole. So 1 divided 1. How many dB?
0 dB.
Perfect. So one dipole has 0 dB D
Gain.
because D stands for dipole. Okay.
The last D.
The last D.
Oh.
Then I'm happy that someone said, "Oh," because we teach you something.
Yes.
So something interesting for you. Now you have seen many times, but now you know. Okay. Then the other question. I put 4 dipoles. What is the dBd gain of a 4 dipoles antenna?
Think step by step, it's easier.
Okay, Kuzani, you raised your hand, you have the answer. Use what you have here written. 6 dB, how
Excuse
many?
Me, I've lost you there. Engineering, I can't get you anymore.
Okay, where? To the fact that a dipole has a gain of 0 dBd. Did you lose your track here or where? Because this is the first assumption where someone else make, oh. Kuzani is no more online. He failed, maybe, his connection, don't know. Let's wait, if not, someone else will explain to him. Now I don't see also the video. Okay, now I see.
I just want to
Okay.
check if Kuzani is offline or not.
No, okay. Kuzani is already here. Yeah. Okay, so Mr. Kuzani, where you lost your way?
Yeah.
Where?
I got lost here when you were talking about the dipole. I could not hear your voice.
Okay. So the first question was, let's define the gain of a dipole respect to itself. So the gain that it is called dBd, gain of a dipole over a dipole, which means in terms of power ratio 1/1, like Puyo is showing. And so the gain in D will be 0 dBd for one dipole. Is now clear?
Yes.
Okay. So the next question I asked you is, if I increase the number of the dipoles to 4 dipoles, what is the total gain of the antenna in dBd? Because we have increased the number, so the ratio from 1 dipole to 4. So the power ratio increase is 4 times. How many dB D has now the whole antenna of 4 dipoles? Look at the first example to calculate how much is 6 dB, and you will get the answer.
Please, engineer, my idea is okay. So we know that when increasing the number of dipole than 2, it means we have 3 dB because we double the gain. So than 4, it means 2 times 3 dB. So for me, it's 6 dB.
6 dBd in
6
this
dB,
case,
yeah.
because in this case your reference is the standard gain of a dipole.
Okay.
Okay, it's clear for every one of you?
There is also another way of resolving this example, step by step. 2 dipoles will double the gain. That means the gain is 3 dBd because double the gain. And 4 dipoles means 2 times the structure of 2 dipoles. Again, doubling the gain, that means 3 dB plus 3 dB means 6 dB. dBd, because we reference to the gain of one dipole. Yes. So 2 ways to obtain, of course, the same result.
This was exactly what I would like to tell. Is this clear? Let's continue. If we double again, Ramadani lost. If we double again the number of dipoles, so with 4 dipoles we are at 6 dBd of gain. Now we go to 8 dipoles.
12 dBd.
No.
No.
We are at 6 and we doubled.
6 dipoles.
Not 6 dipoles.
No.
We are with 4 dipoles, we have 6 dBd. Now we go at 8 dipoles. 8. Who you? 8.
Oh, 8.
Yeah.
8. So we doubled from 4 dipoles to 8 dipoles.
So that means 2 times the power of 4 dipole. A power of 4 dipole is 6 dB. If we double it means 6 multiplied by 2, 11.
But it's not multiplied. This is the fault. In dB. You have to add, not to multiply.
It means 9.
Exactly.
dB,
Exactly.
9.
That was the clue here.
Okay. And I would like to ask you, forget the dipoles now. I ask you, what is...
Please a moment. You said 8 dipole, we're supposed to have 9 dB.
DBD. DBD.
Okay. Yes.
Okay. But now, forget now for a moment dipole.
Maybe here, engineer, maybe he has some question or he didn't understand.
Okay. Go with the question if you have. Is there a question? No, it was.
Sorry.
Okay.
Sorry.
My question is now, what is the power ratio that corresponds to 12 dB? dB is 9 dB plus 3 dB. So it is easy to calculate the ratio. It is the same principle we had in going from 6 dB to 9 dB. Now we go to 12 dB.
So for 9 dB, we have 3.
Can you repeat the question?
Pardon? Could you repeat?
He asked you to repeat the question, please.
Repeat the question, or I heard an answer. The question is...
The question, not an answer.
We are always going from dB to ratio or to ratio to dB. Now my question is, we all understand that 6 dB correspond to 4 dB because we have used the 3 dB, okay, twice. Now we did the same for calculating 9 dB that correspond to 8 because it is 3 dB plus 3 dB plus 3 dB. That it is
9 dipole.
9 dipoles. No. Now I'm asking you to go one step forward, and I ask you how much is the ratio in power for 12 dB, considering that 12 dB is 3 dB plus 3 dB plus 3 dB plus 3 dB, or 9 dB plus 3 dB.
14.2.
How much?
14.2.
Why you said this? It is very easy, more easy.
6.
So 9 dB means 8 in times, okay? I add again 3 dB. Add 3 dB means what? Multiply by
2 times 8. 2 times 8. So 16.
16.
Exactly.
16. Yeah.
Okay. Now very quickly, 15 dB. How much it is?
15 is 9 plus 9 plus 3 plus 3.
The last was 12, that was 16. Now you add again 3 dB. So instead of being 16 is
32.
32.
32.
Oh,
Exactly.
okay. And you can continue. Okay. So if you add every time 3 dB, you go with the power of a 2. 32, 64, 128, etc. Okay, but in the reality, I've never seen an FM antenna with more than 16 dipoles vertically, okay? So now let's go to next step. Pande disappear, so who is next online? David? No, David, Huo. Who is it? Huo. Uwimana, Oscar.
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 Yes, yes, my network
Okay.
is not very good. Yes.
Okay. Now please read the next step of the next value we want to calculate and maybe memorize.
Yes, we can also calculate it 7 dB equals 10 dB minus 3 dB in the power ration domain is 10 divided 2 equal 5.
Okay, is this clear? Minus 3
Yes.
correspond to dividing by 2, and we know this. 10 dB, we remember that it is the same, so 10 dB is 10 times. So 10 times divided 2 equal 5. This means that we have another value. 7 dB correspond to 5.
Okay.
Is here in the table.
Okay, let's add another value.
I go?
Yes, please.
Yes. And also now 4 dB equals 7 dB minus 3 dB in the power ration domain is 5 dividend 2 equal 2.5.
Okay. Is it clear? And now Puyu is showing on the table.
So the table step by step is filled with green, known, easy calculated values.
Okay, but I want to be bad, and I tell you why it is written 9, that it is 7.9 and not 8. I give you the answer. It's question of approximation. Okay, in the logarithmic table, there was approximation, and so adding many times you have a very small error. But use for 9 dB the value 8. Okay, because it's easy to remember and to understand. We will see at the end, we will have an approximate table that I suggest you to use, because it is easy to remember. Okay, let's go.
Okay, and also now 1 dB equals 4 dB minus 3 dB in power ration domain is 2.55
Sorry, I found another typing error. Is 2.5 divided 2. Forget
As
the
it's
second
written
part.
here, 2.5 divided by 2.
Okay.
That's
equals
1
equals 1.25.
Okay, and if you see in the table, it is 1.3, because it is approximated to only to the third figure. Okay.
Okay. Okay.
So we will use 1.3. And okay, read the next sentence.
Okay. At the end, if you want to add 1 dB, just addition 20 dB per 100 to the power ration.
30% to the power ratio. So this is the only strange number we will use because it is not exact or 0.5. So my trick that I would like to tell you is, if you want to understand how much is 1 dB more in power, just add to the power 30%, and you, in your mind, it is easy, I think, more or less, to add 30%. Like if you go on the market and you know that the price is increased by 30%.
Okay.
And now you can read, but I already told you why there are some small differences between this calculation and the table.
Okay. Some Polish can note some small difference between this simple calculation and the tab at the value for 9 dB and 1 dB. Due to the factor that is don't want to go hit that the second decimal figure.
There is also another error of typing the real what that I don't want to go higher than the second decimal figure. Okay, go ahead.
We have now to fill the last 3 values. Let us the values 5 dB. We can put it into the value. We have to remember or derive it is as 10 dB equals 5 dB plus 5 dB. That is the power ration domain is 10 equals Y multiplication Y, where Y is the values you don't know.
So we have to extract the square ratio, the square root.
Yes and no, because you can go for iterative approximation. I would say that typically I use for 5 dB the number 3, because you know very well, going step by step, that 3 per 3 is 9, and 9 is only 10% of difference respect to 10. So I will not. I suggest you to use the easy at the end, the easy value of 3, but you will see written here. You can continue.
Okay, of course, if the square root of the tan is 3.16 approximated to 3.2, you can also use a value of 3. Easy to remember, and 3 multiplied 3 is 9. That is expected to 10 give an error only in the range of the around 10%.
Okay, is this clear? So I made an approximate table Puyo is showing you. So 5 dB, I suggest with a little error, but it is easy to remember that and to use a power ratio of 3.
Now we can calculate 8 dB equals 5 dB plus 3 dB in the power ratio domain is 3.2
multiplied by 2.
Multiplies 2 equals 6.4, approximated as we spoke.
And if you see the last table, of course, I use in reality 3 multiplied by 2 for 8 dB, and so I get 6. For you, can you show 8 dB power ratio 6?
Yes.
Okay. Okay. And okay, you can go ahead. So we get the last value.
Now we have all for easily calculating.
Sorry. We spoke about 2 dB. Puyo, can you show you 2 dB? Okay, so it was 1.6, but I approximated for easy remembering 1.5, that it is plus 50%. Okay, you can go ahead in reading.
Now we have all for easily calculating all the values in dB and the correspondent power ratio, only remembering a few values. I'm not a push. We are research. So let's propose you.
Sorry, another mistyping. We are not researchers.
We are not researchers. So let's propose you the approximate table I have put in my mind as the 7 multiply 8, it's 14, 16.
56.
56, please. Numeric table.
Now, Puyo, return up 1 moment. Okay, for the dB. So in the numeric tables, when you learn at the school, you have to remember something like 100 of numeric tables. In dB, in the reality, if you like, you can remember this table, okay? And you can expertise yourself. Every day you do this, and if you do this for 1 month, typically it stays in your long-term memory, especially if you sometimes use it and refresh it. But remember that in the reality, we have seen that the only one value you have really to remember is the most easy 10 dB equal power over power ratio of 10 dB. And then I have told you how to easily derive all the other numbers. And when you have this, you can easily calculate, for instance, 33 dB. How much is 33 dB? Is 10 times multiplied by 2, so it's 20. Okay, I'm very used to do this, but you have to exercise yourself because dB are your bread of every day. The last one I only tell you quickly how to manage the same table with voltage ratio instead of power ratio. Sometimes you can have to use it, while typically 99% of the time you will manage the power ratio. Okay, Oscar. Oscar disappeared.
Yeah.
Okay, who will do? Again. Okay, Oscar. Oscar, can you please continue? So we said that the same, even if rarely you will use it, but sometimes you can calculate the voltage ratio, and there is an easy way to use the same power tables to calculate the voltage ratio, and I will show you here and explain how.
Question.
Yes, please.
Yeah, the only difference is that voltage is 2 times what we've seen with power. Is that true?
Just read it, but I would like first that we read and then we try to understand, and we can confirm or not what you said, because what your was not a question but more an answer.
Okay.
Okay, Oscar, can you read it?
Yeah. Same method applies if you want to the voltage relation. Playing the formulas only having a difference of 20 instead of 10, the sum table with follow. dB equals 10 logarithm power reference for the power reference, or 10 logarithm
20.
value, 20 logarithm values to various reference.
I would like to reformulate. dB equals 10 logarithm of the power ratios, or 20 logarithm of the voltage ratios.
Okay.
Okay.
Easiest.
Okay. For instance, for erection, in this is case of voltage ration of 10, you will have 10 multiply 2 equals 20 dB instead of the 20 dB for a power ration for the power reference of the 10. For
what Joseph more told.
Okay. For instance, for ration, in this case of voltage reference of 2, you will have 3 multiply 2 equals 7 dB instead of 6 dB instead of the 3 dB for a power ration, for the power reference of 2. Easy to say mathematically, that there is a square of or difference. The power is proportionally to the square of the V simplify V multiply V.
Because I don't want to use the square, so I can double use the multiplication. Okay, at the end, as Joseph said, there is a shift in the table by a factor of 2, because you see that one is 10 log of the power ratio, and the other is 20 log the voltage ratio. And the example clarify, because when you want to know a voltage ratio of 10, that it is 10 dB for power ratio, with voltage you will have 20 dB. So multiply the dB by 2 to have the same ratio.
To try to be more clear, we measure the same system. That means we have to get the same result, expressing it in power ratios or in voltage ratios. Why is the difference of 2? Because in the sample definition of the power, the voltage is raised at the power of 2. Power, its voltage rise at power of 2 divided by the resistance. So this 2 is not something strange, comes from the definition of power and voltages.
Exactly. At the end it is written, the power is proportional to the square of V, simplifying V multiplied by V.
So it's the same result. This is important. You don't measure two different results. Questions, please. It was not easy. I recognize.
Well, the principle, I think it is easy. You have made by yourself, and I think this is the right way to make lessons. So you make the lessons, and so you will be more more active, and we understand where you really understand or not. Okay, Joseph, please.
I thank you a lot for this method. It is very, very, very useful, exceptionally for me. And what I can propose is, as an exercise to be sure everybody understood, is to remake a table with voltage, referring to the table with power, just to remake it in voltage and put new values as an exercise, for example.
Oh, okay. Now we can, I have prepared anyway for you, because maybe sometimes you can put this table in your bags and can be helpful sometimes, where I have calculated a very large table with dB going from 0 till 150 and from 0 to minus 150. But in this respect, sometimes the numbers for the ratio are so incredible high or low that after 1 million or 1 over a million, I have decided to use a scientific notation. So I please Puyu to open it and to scroll it so we can check how it was built. The squared part, you can show you. It is typically the not approximated, so very exact coming from the formulas, and there is both power ratio and both voltage ratio. You can see that in this case, the point where both are the same is 0 dB. Then you can also find more like 13 dB, like we have seen, 15, etc., etc. We remember that 15 was 32, and this is not approximated, it is 31.6, but 32, of course, is very, 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 very acceptable. Then if you go down, you see that in the positive part of the dB, the number starts to be high. Will you go down, please? Okay. After you see that there is a change. Pull you a little up. After 1 million. Oh no, I decided. So I decided. Yeah. Okay. I was reading the voltage, and so it was only 1000. So after 1 million of power ratio, I decided to go in scientific notation. And now I would like that one of you explain us what means 1.3 E plus 0.6.
1.6 E plus 0.6 mean 1.6 exponential 60. So 1.6, that was the first question I asked you to know how to translate in English. But in French, it is 1,3 puissance million.
Okay, 6 is the power of 10, and at the end is the number of 0 that are after the first figure.
That's the number of zeros to be added after the first figure.
1.6 in this case. Okay.
So this is 1.6 million here. This is 1.3 million here.
Yes.
This is 4 million here. Million because there are 6 is the power of 10.
Yeah. But I also stopped at 60 because 60, if it is the respect, no, Puyu, stays at 60 dB. Okay, 60 dB is 1 million, and if it is watt, 1 million is 1 megawatt transmitter. So this is the reason why I stopped here, because I have seen a couple of megawatt transmitter, but no higher so far. On the opposite side, on the minus, you see that there is minus 60 is 1 with minus 0.6, minus 60. Okay, and this means 0. Other 6 figures after, and so if you don't express in itself, it is a number that you cannot understand because it is plenty of zero and
Have you ever seen, engineer, have you ever seen this power in a system?
Pardon?
Have you ever seen such power, such low power in a system?
Absolutely, yes. Low power, a spectrum analyzer can read, or a receiver can read a signal and receive a signal in the range of minus 140 dB.
Okay.
Minus 140 dB. But even you, Joseph,
Yeah.
so in one of my last videos, the carrier of 16 megahertz from the offline receiver, it was minus 77 dB. DBM.
Okay, let's now going up. Because you see that there are values in dBm. What means M?
Milliwatt.
Okay, it are dB referenced with a power of 1 milliwatt. And then you have the milliwatt correspondent for positive and for negative values. Okay. Again, after minus 30, I started to use the scientific notation because too many after 30. No, go at 30, not 60.
30, sorry.
Maybe because
yes.
1 milliwatt, it is a small quantity.
So okay. Minus 30 here.
Yeah. That it is 0.001 milliwatt. And then I started with the scientific notation. With dB watt, let's go on the other table. dB watt we only use as positive. So 0 dB watt is 1 watt. Okay. And I didn't put the second figure, so also 1, it is
1.3.
1. Okay, I didn't put the point. Okay, but as soon as you reach plus 30, you are already at 1 kilowatt. 30 is 1 kilowatt. 40. Let's see 40, Puyo.
10 kilowatt.
40, it is 10 kilowatt. It is already very high. 30, it is 100 kilowatt. 50 is 1. 50 is 1. No, 50 is 100 kilowatt. And 60 is 1 megawatt. Okay. So typically in practice, this is more or less highest power, but I continue the table because it was easy for me. But the values are so astonishing that, okay, but I just put it, who never knows.
Questions, please.
You can print and bring this table to you and put it in your bag, maybe.
In your smartphone, because it's a small table.
Okay. Please take into account that the screen of the actual spectrum analyzer ranges 100 dB. So look at how much is 100 dB. For instance, you can show you.
Just a moment. It's here.
And they can range even more because they have attenuators. So they can range typically 140, 150.
We talk about, let's say,
dB.
minus
Yeah.
100.
Yeah.
It's 10 at the power of 10. 100 dB.
Okay. Maybe you can exercise yourself in making a table of dB over microwatt, that it is 1 million of watt. Okay, this is our bread that we have to use every day. It was a long lesson, but I think doing by yourself